everybody. Today I would like to tell you about how we managed to prepare new free fluoride or naked fluoride reagent derived from persistent N-heterocyclic carbenes. This is part of my research work, which I'm doing under the mentorship of docent Dr. Jožef at the Department of Inorganic Chemistry and Technology at Jožef Stefan Institute. So, if we take a look at overview, firstly, we're going to see what are the established methods of preparation, the easiest, of imidazolium fluoride, and the problems this path has. Then we're going to see how we can solve these problems with reactivity of N-heterocyclic carbenes with HF sources. Then we're going to see what NMR analysis can tell us about this system. We'll see that we have some kinetic control of a reaction and thermodynamic. We're going to take a look at the whole reaction scheme overview, touch reactivity, and end with conclusions. So, the easiest way to imidazolium salts, to imidazolium halides, is if you take imidazole substrate and react it with organohalide. What happens is you get quaternization of nitrogen atom and halide as counter anion. But this reaction works only with iodine, bromine, and chlorine, not with fluorine. Of course not, that would be too easy. And the reason is because CF bond is too strong and this reaction doesn't take place. So if you want to then prepare imidazolium fluoride, you have to do additional step with fluorinating reagent, so metal fluoride. And this step has some problems. The first one is the solubility of metal fluoride in use. Because metal fluorides are scarcely soluble in organic solvents, you usually have to introduce water to the system. And this is not wanted because if you're trying to make a new fluoride reagent, F- is highly dependent on its environment. So water usually deactivates its activity and reactivity. And the other thing is you get, by doing substitution reaction, you get, of course, your product, but with it another MX salt. And the research on this field showed that it is problematic to isolate pure anhydrous imidazolium fluoride species. So what we envisioned is, why don't we go by established synthesis procedure from imidazolium halide salt to N-heterocyclic carbene moiety, and then do not substitution but addition reaction of HF to the system. And I did this reaction. I took carbene and reacted with anhydrous hydrogen fluoride as a solvent and as a reagent, and just hoped it doesn't destroy my substrate, it doesn't burn it or react in a different way. Luckily, it didn't, but it didn't give me imidazolium fluoride either. But what it gave me is imidazolium polyhydrogen fluoride. Now, that's nothing special, but I've managed to prepare crystal structure of it, but I would just like to point out that this is not a fluoride reagent. If you dissolve and use this reagent, the two HF molecules get dissociated, and so this is the acidic reagent. We don't want it. But we were kind of on the right way, because if with surplus or 3 equivalents we get polyhydrogen fluoride, then the question arose, can we then, by stoichiometric quantities, with 2 equivalents get B-fluoride species and with 1 our wanted product? And here we had another, we encountered another problem, and that is AHF is a nasty reagent and nobody wants to use it. So I was trying to find an alternative for a better reagent. And when I was doing the research, I stumbled upon 3-ethylamine 3-hydrogen fluoride complex. Now, this one has potential. I mean, you can go and try to do the reaction in glassware with anhydrous HF. You cannot. You can prepare a standard solution out of it, and the handling is easier. And again, I did the reaction with surplus, and I got the same result, which was awesome. And then, luckily, with 2 equivalents, I managed to obtain p-fluoride, and finally, with 1 equivalent, I got my wanted imidazolium fluoride reagent. Now, here the crystal structure, which is also interesting for several reasons, but I don't have time to go with it. And here is our F- loosely stabilized by 4 hydrogen bonds in a crystal structure. But the interesting thing start to happen not in crystal structure but in solution. So first of all, I would like to show you NMR spectrum. So these are 3 different superimposed spectra of purified species. We can see far right we get singlet peak for average signal for all 3 F-, so for dihydrogen trifluoride anion. On the other side, we get a doublet signal with characteristic HF copy constant of 115 Hz, which can also be seen from proton spectra, and it's characteristic for B-fluoride. And just 1 ppm higher, we get singlet peak for imidazolium fluoride. Now, why am I showing you this? I'm showing you this because I've grown monocrystals of imidazolium fluoride. And I took it to X-ray analysis, got parameters for the crystal set and everything, and then dissolved the crystals in a deuterated acetonitrile. And when I took this sample to NMR, I got this signal. Now this is strange because this signal corresponds to B-fluoride species, and this confused the hell out of me. But with some time, we were able to figure out that sometimes you just have to leave things alone in chemistry, because after 24 hours in the solution, the doublet is gone, and we again get a singlet peak characteristic for imidazolium fluoride. Now this suggests something I think is quite interesting. 2 imidazolium fluoride in acetonitrile, they react and form B-fluoride and free carbene species. With additional time, the reaction goes back, and this product stabilizes in the solution. Which, if you think, is quite interesting. 2 imidazolium salts form free carbene moiety. Now, this type of chemistry hasn't been observed before. And we can see that on the right we have kinetically controlled products, and on the left thermodynamically. So if we take a look at the reaction scheme now, because of 1 transforming into 2 and back, we said, well, of course, if we synthesize pure imidazolium B-fluoride species, will that, with addition of equivalent of carbene, go to monofluoride species? And of course the answer was yes. But then we ask ourselves, well, we know 1 single compound, fluorocompound, that is not harmful, is stable on the air, and is widely used in industrial level, and that is potassium B-fluoride compound. And we said, what if we react carbene with potassium B-fluoride? And the reaction got us the same results. So now we have a really easy, basically easy, gram or 10 gram synthesis of pure anhydrous imidazolium fluoride. Potassium fluoride that participates out of the solution is not soluble. It's not soluble in acetonitrile. We weren't able to get any signal from NMR spectra of these species. So elemental analysis, everything showed that it is pure. So that was that. What about reactivity? I reacted imidazolium fluoride with iodine benzane. So there are, what we have to know, like I said before, is F- is highly dependent on its surrounding. So if it's active, the research showed it has strong basicity as well as strong nucleophilicity. So it has competing reactivities. And this is the spectrum I got. Here is our unreacted product, but here you see this peak. But also because fluorine NMR is highly sensitive to impurities and other compounds, this is not isolated system, so we have everything in the solution. I cannot and I cannot tell you for sure which one, which species this is, but it doesn't matter. I'll tell you in a minute why. I also reacted with deuterated chloroform. What participated out of the solution, and we got crystal structure is imidazolium chloride, so it's active, and we got mixed halogenated species in the solution, and the same goes for tetrachloromethane, which is even more reactive because no peak for imidazolium chloride can be seen, but mixed halogenated species was observed. So that what's the point? What's the whole idea of this presentation? Well, the point is that the species is active. It is reactive, but its reactivity and full scope of utility is yet to be researched. So with that, I would like to appeal to anybody here. If you want to use this compound, which we can make on a large scale in biological, organic, inorganic, or even material systems, somehow you will find that the doors of K1 department will always be open for future collaboration. I think that's a good point to end with. So with that, I would like to thank especially my mentor for all the time and energy he has given me. God knows that's a lot. And to everybody else, of course, who participated and who's sharing this experience with me, and to you who kindly persisted through this lecture.